for linear regression. So linear regression is just about finding a best straight line to find relationship between the input and output variables. So to explain this, let's take a scenario where we have a couple of students. So we have the data for them, which tells the scores which they get, which is the output variable, given that they study for certain hours, which is the input variable. So let's assume the more hours they study, the better scores they get. So that's why we have this data point. So it is like increasing with respect to the more hours they study. So here we have to find a best fitting line which helps to find the relationship between the input and output variable, which are these data points. So let's say the predicted line is this one. So at this each point in this line, we can predict the study hours and the corresponding scores. So let's say we have a point here on this line. So this corresponds to 5 study hours. So with this line, we can predict the score which he would get. Let's say it's 90. So with this line, we can represent the relationship between the input and output variables. So we can see that in these data points, the line what it tries is to get the best fit, so such that it can explain the relationship clearly. So what do I mean by this? So assuming the points are in a straight line, let's say the points are like this, just the straight line will be enough to fit these points perfectly. But if the points are like this, we cannot fit it perfectly. So we need to find the best fit line. So that's why we find the best fit. So data is not perfect like this in real world scenario. So the vertical difference, the vertical height between the predicted line and the data points is called residual. It's a kind of observed error residuals. So these are the errors represented by E. So we need to take this into the account. So you know that line can be represented as this equation y equal to mx plus c, where epsilon represents the true model's error which we added. So here y equal to mx plus c, you know that m is the slope. So slope value explains for unit change in x, for how much the value of y changes. So if m equal to 2 for unit change in x, the value of y changes 2 times. So it represents the steepness of the line. So if the m is bigger, the line will be very steeper. So if the m is negative, the line will be steeper on the downside, on the downwards. So we have the intercept. Intercept is where the line intersects on the y-axis. So it is in other words, is the value of y when the x is 0. When the x is 0, it's the value of y. Let's say the line is like this. It intersects here. Let's say this point is 3. So it intersects at y equal to 3. So this is the intercept value. So using this intercept and slope, we can shift this line anywhere we want. What do I mean by this? So if we want the same line, let's say like this, if you want this line like this, we can just shift it. We can uh, adjust its slope and intercept such that it can be shifted from here to here. So we or let's say we want it here like this, we want it more steeper. So if we want it more steeper, we can just adjust the slope let's say like this, we can adjust the slope so that it will be more steeper, and hypothetically this if we extend this line, it will intersect here. So if we adjust the intercept, we can get this line. So similarly, we can get in line, we can manipulate the line anywhere we want. So that's what the model does. It can move the line anywhere it wants, such that we find the best fitting line here. So that's what is represented by this equation. We have the y, which is dependent variable. So dependent variable is the output variable, and we have the independent variable or variables or the input variables we use to predict the output. So we have, in order to find this line, we need to find, or we need to find any line, we need to find these two values, which is the slope and intercept. So in order to find this, we cannot find like a random line. We need to find a line such that it best fits these input data points. So in order to find the estimates of this M and C, we use a method called ordinary least squares, which we will see next. So let's see how we can find the values of M and C, which is our answer for the variables using OLS, ordinary least squares. So here we have the predicted value, which is represented by y cap, which is the predicted line y equal to mx plus c. Let's say this is the predicted line, and here we have the data points. So residuals, represents the vertical distance between the actual data points and the predicted values of this line. All the predicted values lies on this line. So we can calculate the residual or error for each data point. For each data point means we can represent it as y cap of I. So normal yi means the actual values. So error residuals can be represented as the difference between actual value and the predicted value. If we find difference between these two, we'll get the value of the error. So that's what is being done here. If we just subtract these two, and we will get this one, in turn we can substitute the value of the value here, which is the line representation. So after calculating that, we need to find the sum of squared errors. So why do we need to find that? Because only after finding that we will get a function. So we can calculate the value of m and c, which is crucial for finding the best fit line. So we have to find the value of the m and c such that this equation, this cost function, which is the sum of squared error, is minimum. So only if the error is minimum, we can find the best fit line of m and c's, because if the error is minimum, they'll be lying close to the data points and the error can be minimized. So that's why we need to find this function. So why do we find the square errors of the squared errors instead of just errors? Because errors can be positive or negative. So if we just add the errors together, they might cancel out. So that's why we need to take the magnitude. So we take the square. So after taking the square, we just take the summation in order to add all the residuals. So after we get the cost function, now we have to minimize that. So in order to minimize this function, we need to take the derivative, and we have to equate the derivative to 0. So 1. So only after that we will get the minimum value for the variables. So here we have two variables, that's why we take partial derivative. So if we have just one variable, we can just equate the derivative equal to 0. So why do we do that? So let's say we take a function f of x equal to x minus 2 the whole square. If we take the derivative of this with respect to x, we will have 2x minus 2, and if we equate it to 0, we will have the x value as 2. So this is the value for this function. where we'll get the most minimum value. So if we put 2 here, we will have 0. So obviously 0 is the minimum value we can get for this function given any arbitrary value of x. So that's why we do the derivative, but this is for the one variable. So if we want two variable, we will do the partial derivative with respect to the both of these variables for the sum of square function, and we equate them to 0. So that's what is being done here. So here we have the same function. If we take the derivative, we have the 2 here, and we do the partial derivative with respect to c. Here we do the partial derivative with respect to m, and after doing that and equating it to 0. So first things first, here we have the summation of yi alone. So we will take this to the other side. So if we take this to the other side, you'll have this equation. So here in this equation, if we do the chain rule here and simplify this, we will get this one. So just because we have the summation over n times, we have n times the constant, and if we rearrange this equation, you will get the constant c intercept. So we'll get the intercept as this equation. So similarly, we can do the partial derivative with respect to m slope on this equation, and if we apply the chain rule and if we expand this, we will eventually arrive at this equation. So here, while doing the partial derivation, we will use this equation to substitute in order to achieve this. So this is the final equations for the c, intercept c, and the slope m. So here we can see this corresponds to the covariance of x and y, and summation of the actual minus mean value the whole square is just the variance. So that's how we get the values for m and c in order to get the straight line. We just saw how to do simple linear regression. So we have the b0 and b1. This is the intercept and this is the slope, output and input variables. So here we have only single output and single input variables. So what if we have more than one input variables like x1, x2, and so on? So that for each independent variables we need coefficients. So in that case, in order to do that, we will do that using multiple regression. Matrix comes in handy in order to represent and solve this. So put in an equation, the input equation. So here we have the yi, which is the output values. So this can be represented as the sum of the coefficients and the slope multiplied by the input values. So here we have xi1, xi2, and so on. Because it's multiple regression, we have multiple input values, and we have beta 1, beta 2, and so on. So for each input value we have the coefficient, and the beta naught represents the slope. So the same equation can be represented in this matrix form. So here we have y equal to x beta plus e epsilon. Here this is the error vector. So this is a matrix equation. Here the y is nothing but the output variable values. So output will only be a single value, but we have it for the whole entire data. So if we have 500 data rows, we'll have 500 output variables. So the number of, let's say the number of data is n, so we have the dimension of y vector as n times 1, because we'll have only one output for each data row. Next we have the matrix X, which is represented here. So the shape of this matrix is n times p, where n is the number of data and p is the number of parameters or number of features. So think of it just like the table format, where we have the name of the feature in the top as the column header, and we have the serial number 1, 2, 3 for each data row, and we have the corresponding data like in an Excel sheet or something. The same thing is represented. So we have n number of rows, that is n number of data. So we have all the data here, and the number of columns is the p is the number of parameters. We have parameter 1 to parameter 2 and so on. So you can just imagine like the data will just be like here in a table format. So also if you notice that the first column is full of ones, so we have one in order to match that during the matrix multiplication with the intercept here. So let's see it in a. So now we know about the shape and contents of the matrix. Let's go for the matrix vector beta. So here the vector beta is a coefficient vector which is of the shape p times 1. P is the number of parameters. So for each input variable we need that many number of parameters. That's why we have the shape as p times 1. So here the first one, b naught beta naught, is the intercept value. So the intercept here, when we do the matrix multiplication, it must be handled by multiplying with the 1. So if you multiply the matrix and the vector, the first element is multiplied with the intercept value, so which is 1. So that's why we have the first column full of ones in the matrix X, because in the equation the intercept is not multiplied with anything, right? So that's why it's multiplied with 1 here, but in the other case we multiplied that with the input data inside. So that's it about the representation of this equation in the matrix form. So similarly we have the predicted values. So while predicting the values, we don't get the error. So we just have the multiplication of this matrix and this vector, the X matrix and the coefficient vector. So here we need to find the coefficient vector. So that's what we need to find. So in simple linear regression, we will represent the sum of square errors as this equation, which is a summation of the difference between the actual and predicted value square. So when we come to the matrix form, so we have the error from this equation. We can find the error. So epsilon is nothing but, if we take this to the other side, we'll have y minus x beta. So this is the error. So we have to square this, right? If we square this, we can get the error, but this is a matrix. So in order to square a matrix, we just need to multiply it with this transpose, because only then if we multiply it uh, like this way, we will get the diagonal values where we have the square of the matrix contents. So if we substitute the value of the epsilon and its transpose, we will arrive at this equation. So here we have y minus x beta transpose multiplied by y minus x beta. So this is our cost function. So here if we expand this in the quadratic form, we will have this one. So we need to minimize this, right? So here notice that we have beta. So if we do the partial derivation, on this equation, we will arrive at this equation. So after derivating, you have to equate this to 0 in order to find the minimum. So if we equate this to 0, we will get this equation. So if we rearrange them, we'll finally get this coefficient vector as x transpose x inverse and x transpose multiplied by vector y. So that's how we can get this coefficient vector. So here we have the first value, which is corresponds to the intercept, and rest values we can get the coefficient, and eventually we can form the lines. Now let's look at the Python code for linear regression, which is pretty simple. Here we have the input and output data in an array. So first step is we need to calculate the mean so that we can find B0 and B1. So after finding the mean, we need to calculate the slope B1 and B0. So first for B1, we have the formula as summation of xi minus mean of x multiplied by yi minus mean of y in the numerator. So first you have to calculate the numerator separately, and we have to find the summation, and then we have to find the denominator separately for each, then you have to add them both. Only after then we need to divide. So given that we need to calculate the numerator and denominator separately, first we just initialize them to 0, and we just iterate it through every value, and we just calculate the numerator from the formula, and then we calculate the denominator. So this is nothing but the covariance of x and y, and this is the variance of x. So after calculating that, using that, we can get the value of v1. So for v0, the formula is just mean of y minus slope into mean of x. So if we substitute that, we can get the slope and intercept values. So using this, we can get the output variable for a given input variable. So this function is used to predict the output variable. So if the user gives the input value as 6 or any arbitrary values in order to predict with linear regression, so this goes into this function, and using the calculated values of b1 and b0, we can get the output variable value, and it is written here. So here, this is how we do that. So here we enter the values 6 and 2.5. We can get the corresponding predictions and the slope and intercept for the given input data. So you can see the visualization. Logistic regression. So previously we saw linear regression, which is used to predict continuous output variables. So we can predict any value between minus infinity and infinity with the straight line. So in case of logistic regression, though the name is regression, we use it for classification tasks. So we classify items. So whether it's a dog or cat, or let's say a person is having a disease or not, with the help of the input features. So the input features or the predictor variables can be anything. So if we decide if a person is having disease or not, let's represent it as 0 or 1. So this is a binary outcome. So the input features can be anything like the pH of the blood, or any presence of microorganisms on the blood, or so on. So all the predictor variables, using logistic regression, we're gonna classify if a person is having disease or not. Why not use linear regression for the same task? So yes, as we see, the linear regression output is always between minus infinity and infinity. It is a line. But what we just need the output to be either 0 or 1. if the person is having disease or not. So clearly you can see there are values which can be predicted which has negative values or values more than 1. So this is not the real case in case of classification because we just need it to be 0 or 1. These are nonsensical values if it's negative or more than 1. So in that case, we use logistic regression. Another thing is that it is more sensitive to outliers. This linear regression model is sensitive to outliers, and the error metric which we used in the linear regression is sum of squared errors (SSE). So this treats all the errors equally, either large or small errors. It treats all them equally, but in case of classification models, we need to treat the large errors with more penalization, and we need to treat the less error with less penalization, which is not done by the linear regression model. That's why we go for logistic regression. So here we can see the standard definition for logistic regression. It is a statistical method for binary classification. It models the probability of a class using sigmoid function applied to a linear combination of the inputs giving results between 0 and 1. It is being repeated. So it models the probability of a class using logistic or sigmoid function. So the single class which we take here is we can take if the person is having disease. So it models this probability using sigmoid function. So here we have the sigmoid function. So what is a sigmoid function? We have this 1 by 1 plus e, which is the base of the natural logarithm, minus z. So z is nothing but the linear part which we saw in linear regression, which is the multiplication of the coefficient and the features added together along with the intercept. So this is essentially the linear part which we calculated in the linear regression. We use the same thing here. So what this does is it transforms the original inputs. So we have the original data between minus infinity and infinity. It transforms them and fits them into a S-shaped curve, which is a sigmoid curve, and it has the value between 0 and 1. So this allows to interpret the probability more than just the actual values. So this set corresponds to the linear part here. So you get the transformation, the essential part which is used to transform this linear function into the S-shaped curve, which is used for interpreting the probabilities in a meaningful way. So here, if z is negative, can be possible in the linear function. So if it is negative, the sigmoid output reaches to 0. So that in that way, it doesn't go negative actually. Similarly, if the z value is 0, we have the sigmoid function output as 0.5. If we have it as positive, we will have the sigmoid output as 1. Just for the sake of explanation throughout this video, I might say the x subscript I or x superscript I directly as xi or x of I or something. So, but we just need to know what it actually means. So, if we have x superscript I, which is denoted by this one, it tells about the ith row data. So, we have many rows in the data set just like in table. So, if you want the first set of observed data for each feature, so it is mentioned by this superscript x of I. So if we have x of I, fifth row we take into consideration of the fifth row, and 6 means sixth row, and so on. So when we have subscript I, which is we write it below. So when you have this thing below, this thing represents that we refer to the element or a feature within a single data point. So if we have a particular row, we have just say this is the first row, and we have many features, right, like x1, x2, and so on. So in order to denote the particular feature, we write this as subscript. So in order to combine this both, to select a particular row in a particular column, so particular row means we write the superscript we have here. So particular column or particular feature, let's say j, we write it as j. So combine, this is the combine notation to denote both. The next thing is we have theta. Theta is nothing but the parameter vector, or these are the values which the model learns. So if you have many features, you'll have many parameters, theta 1, theta 2, and so on, and theta naught the bias. So next thing we have is alpha. Alpha is nothing but the learning rate. So the learning rate tells us how fast the model moves on the direction of the global minima, how fast the model learns. So next thing we have is the inverted triangle symbol here. So it is called nabla. So it is a gradient operator. So this gradient operator tells us about the, it is a vector. So of all the partial first derivatives of the cost function, first partial derivatives of the cost function with respect to the parameter. So we have this cost function partial derivative with respect to the parameter, which is the gradient itself. Next one is sigma, which is just the summation, and after that we have the capital pi, which is the same thing as summation, but instead of adding together we just have the product. We just let's talk about logistic regression in detail. So first let's take an even where we need to determine if a disease is present or not, 0 or 1. So we have a set of input features, like if the blood is having any microorganisms or not, or we have the numerical pH level of the blood, and so on. So these input features are represented by this x variable. We have x1 to xn, and similarly we have w2 to wn, which are the weights or the coefficient, and w0 is the intercept of bias. So this is essentially the linear equation which we saw in the linear regression model. So using these values, we calculate the value of z, and after that, we plug the z value inside this sigmoid function. So this function outputs the probability, so it can be later used for logistic regression, which we're going to see. So how can we represent this linear relationship into this sigmoid function? Let's see the intuition behind that. So in order to understand that, we need to understand two concepts, odds and log odds. So what's a probability? Probability is nothing but a numerical value between 0 and 1, which tells about the chance of an event occurring or not. So let's say in a bag we have red and blue balls. We have 5 red and 7 blue balls. What's the probability of picking a red ball? It's 5 out of 12. Number of favorable events by total outcome. Similarly for blue, we will have 7 out of 12. So this is the probability. So let's say if you want the odds of a favorable outcome. So let's say we need to calculate the odds of the favorable outcome where we pick the red ball. So this is the favorable outcome. The formula is simple. It's the number of occurrence of favorable outcome by non-favorable outcome. So what's the non-favorable outcome here? It's the blue ball. So the odds would be 5 out of 7, while the probability, it will be 5 out of 12. Similarly, if we calculate the odds of picking blue ball, it will be 7 by 5, because the unfavorable outcome is right here. And similarly, for probability of blue, we'll have 7 by 12. So you can see that the probability value, it is between 0 and 1. But the odds value, it will be between 0 and infinity. Why? Because in this case, here it will be a decimal value, and in this case it will be above 1. So it can extend from 0 to infinity, while this will be between 0 and 1. So here we have the odds formula, which is number of favorable by unfavorable even. The even which we chose here is the ball being red. So here we have the 5 by 7. This is the probability of the ball being red and blue. So if we divide this both, this 12 and 12 will be get cancelled, and you will have 5 by 7 remaining, which is nothing but the odds itself. So the odds can be represented as the ratio of the probabilities of the events, red and blue. So blue is nothing but 1 minus probability of red, which is the other event. So this is the final formula. So in a generalized way, we have p by 1 minus p of any event, which is represented by this odds formula here. So here the event which we take into consideration is the person having a disease, which is y equal to 1. This is output equal to 1. So now that we saw the formula for odds and what is odds of a event, we can see the range value of the odds function. We have the number line here. You know that the odd ranges between 0 and infinity. Here we have the value 1. So if the odds are perfectly equal, 5 by 5, in that case you will be having 1, which is the midpoint. And if the odds are in favor of the even, we'll have positive value in the numerator. The numerator is bigger, let's say 30 by 2 or 50 by 2. Here we'll have 15, and here we have 25. On the other hand, if we have the denominator bigger than the numerator, that is the unfavorable outcome is more. So let's say 5 by 100, we'll have 0.05, and let's say 50 by 100, 0.5. So clearly you can see that the favorable outcome ranges between 1 and infinity. The unfavorable outcome ranges between 0 and 1. 0 and 1 and 1 to infinity. You can see there is a big mismatch in the range, because this is a lot bigger, so, and this is a lot smaller. So in order to equalize that, we need to take log of this odds. So that's why we go for the log odds. So let's represent the number line for the log odds. So it is a transformation which helps us to represent this into a number line between minus infinity and infinity. How does it occur? So this is the number line for odds, and this is the number line for log of odds. So log is nothing but the natural log to the base e of any value x. So let me just pull up the graph for the natural logarithm. So we have the natural logarithm graph here. Here you can see that the value ranges from minus infinity to infinity. When the x value, here this is the natural log, and the x value is 0, the natural log of 0 is the x value is 1, the natural log of 1 is 0. So that's why 1 is converted into 0 in this log of odds function. And for decimal values in the original value, which is x, which is substituted as x from the log function, from the odds function. So let's say 5 by 7, which is present here, and let's say reciprocal of this is the 7 by 5, which is odds in favor. It's present in this side. So if we calculate the natural log of this one, it will be minus 0.336, and if we calculate the natural log of this one, it will be 0.336. So you can see that they are equal in magnitude, only the negative value is different. So similarly, for each value in this original odds number line, we can transform it into equally equivalent another log odds number line, where it ranges from minus infinity to infinity. So why is this significant? Because in the linear regression model which we saw before, where we represent the z in a linear line, There also the range is from minus infinity to infinity, and the log odds is also minus infinity to infinity. So that's what makes it significant to use them in the logistic regression. Let's move on to the mathematical part. Here we have the log odds equation. Log odds equal to natural log of p by 1 minus p. So we have this here, p by 1 minus p. It is also called as logit function because it inputs the probability values. It inputs the probability values here, and it gives us the output as a numerical value between minus infinity to infinity log odds, which we saw before. So this minus infinity to infinity is important for a linear representation, as we saw in the linear regression, just a single line which extends from minus infinity to infinity. So this type of representation can be easily modeled, understood, and optimized by machine learning models. So that's what is used in linear regression here. So we know that this logic can input probability and output the values between infinity and minus infinity. We can make an assumption. So this is the main assumption of logistic regression. So the main assumption is that the linear combination of the inputs, we have the weights and the coefficients multiplied by the features added together along with the bias. This is it. This linear representation is equal to the log odds. This is the main assumption which we keep here. We also saw that they have the same range, minus infinity to infinity. So if we substitute the formula for log odds here, which is natural log of p by 1 minus p, here we just ignore the symbol for the variable even y equal to 1. So if we exponentiate the both sides, we will get e power z. This natural logarithm will just go if we just exponentiate, and we'll get e power z equal to p by 1 minus p. And if we just rearrange this, and if we keep p on one side, we will get this equation. So in order to keep the generalized form of the sigmoid function, if we just divide the numerator and denominator by e power z, this will be 1, this will be 1, this will be 1 by e power z, which is e power minus z. So that's how we get the formula 1 by 1 plus e power minus z. So if we see here, we just started with the assumption that the linear representation is equal to the log odds, and we arrived that the probability is nothing but the sigmoid function which is present here, 1 by 1 plus e power minus z, which we get here. So this is the main derivation or the main information which we get. So this relationship is the underlying principle that makes logistic regression output interpretable as probability values. So what do I mean by that? So this relationship allows us to use a simple linear equation like simple linear representation Z to model more complex and non-linear relationship. So this log odds is which we get is from the probability values. So non-linear relationship is like the probability S-shaped curve which we have here, which is between 0 and 1, which has the probability values. So this relationship allows us to use simple linear models in order to represent those complex relationships. So it also tells that we can convert the linear output back into probability. So we have the linear output set. We can convert them back into probability with the log odds formula derivation. So we can just convert it back. So what do we get from that? So this transformation is crucial because while the probability bp is limited to 0 and 1, this is the range in which it can happen. The logit has the range of minus infinity to infinity. So this is what allows it to be modeled by the linear equation. So the linear assumption is very crucial. So that this z is just an equation. So why not use a simple linear model? Because in that case, the values are bounded between 0 and 1, so that we cannot like expand it to from a minus infinity to infinity. So here we can see that the values. This is its shape curve of the sigmoid function, and this is the logoth, which is logoth line, which is from minus infinity to infinity. So we can transform this, and we can use this values to get back the probability by using the logit function. Also, this is a non-linear relationship which yeah, cannot be comprehended by linear models. So in short, this relationship states that a linear model output Z is transformed back into interpretable probability using this relationship. So we can transform the linear model output Z, which is calculated from here, into probability from linear to non, which can bridge the value transformation between linear values and probability world, allowing us to classify an observation. So while using this conversion, we can use them to classify any observation, whether the disease is present or not, into this probability domain. Now let's talk about the maximum likelihood estimation. So it is a key method in order to define the cost function in case of logistic regression. So in linear regression, we had OLS, ordinary least squares, but it is irrelevant here because our current function is a S-shaped curve and it ranges from 0 to 1, while OLS only accounts for values between minus infinity and infinity, and it doesn't account for the non-linearity. So that's why we use the MLE. So here we have the sigmoid function, and here we have the logit representation of the probabilities as the linear combination of the coefficients and the weights. So it's represented by this theta. So theta 1 up to theta n are the weights, and theta 0 is the intercept bias. So let's look at the probability for a single observation. So for a single observation, we have this formula. So what does this formula say? Here we have the probability of yi, conditional probability xi, semicolon. We have the theta. Theta is nothing but the coefficients which are represented. So this is for a single observation. So yi, what is yi? Yi is the actual label present in the data. So it can be 0 or 1. For the ith data, so we have many rows in the data, like for like 100 rows or 500 rows. So for each row we represent it as with the variable I for a particular observation. Xi is nothing but the input features on the ith data. So in the ith particular row we have the output variable in the yi and the input features in the xi input features. Just write IP. So the theta is the vector of model coefficients. So this is the vector of the model coefficient. It has every coefficient which is present here, the thetas. So this is what we are trying to learn. And on the right side, so this can be represented as, it can be put into words like, what's the conditional probability of finding the actual label 0 or 1, given that, on the condition given that we have these inputs, we have the particular inputs I for the ith row data input, given that the probability distribution of this vector is nothing but the coefficient. So this is what gives the probability distribution. On the right side, we have h theta xi. So what is this? This is the predicted probability from the sigmoid function. Here we have, right? So here we input the linear representation and we get the probability value for each. So that is the predicted probability which we're gonna plug in here for every data. So this is for a particular data. And here we have the 1 minus the same data. So what do I mean by this? Why do we write 1 minus the same probability? So here we have the output probability is either 0 or 1. So y can take the values either 0 or 1. Let's see what happens if we plug the y value as 0 on the right side. If you plug the y value 0 on the right side, this will be 0 and this will become 1 and this will be cancelled out. And here we have just 1. So we'll be having just this term. which is when the probability is 0. So it is nothing but 1 minus the predicted probability. On the other hand, the probability of becoming 1 is just the probability itself, which is h theta of xi for ith data. For 0, it's 1 minus this thing. So that's what is happening here. It's like a Bernoulli distribution. So this this equation acts like a switch. So if we have the output predicted, which is output actual label as 0, this term will be activated, which is 1 minus the predicted probability. So if we have it as 1, this 1 minus 1, this will be 0, and this value will be activated, and we'll get the formula for this corresponding single probability observation when the output is 1, actual probability is 1. So it can be used to alternate between these two. So we have the same thing here. So that's why we represent it in this way. So now that we know the probability for a single observation, move on to likelihood function. So what is a likelihood function? What is a likelihood? So this is the function which is represented by L theta. So what it basically does is it measures how well our model parameters theta explain the entire data set. So we want to find the values of theta, which is the parameters which is obviously need to be calculated, such that it maximizes the value of this likelihood function. So this output of the likelihood function must be maximized. So in that terms, we need to find the values of the parameter theta. So it's different from the probability. So in probability, we just have the parameters with ourselves, and we need to find the output value. So let's say if a coin is biased heads and tails, there is a bias such that heads appear 0.8% or 80% of the time, which can be represented as 0.8, and tails appear 20% of the time. So this bias here is given as the input in probability. So here clearly you can see the bias is 0.3 because the original probability of the occurrence of head and tails must be 0.5. So here, but it's 0.8. So we have this value 0.3 as input. So using this, we can calculate the probability of the output from this original calculated probabilities of this heads and tails. So if we add these two, we will get 0.8. So we have the parameters, which is the bias or weighted coefficients. So here in this case, we have the bias. So if we have this value, we can predict the output. But on the other hand, for likelihood, we have the output and we are asking what is the value of the bias or parameters here in this case. What's the value of parameters? So that's what we are doing. We are asking what is theta. So we have the output here already. So using this function, we are asking like what's the most probable parameters, so such that the observed observation is more probable to occur. So you're asking what can be the values of the parameters theta such that the observed data is more probable to occur. So that's what it tells about. We want to find here the value of theta that maximizes this whole likelihood function. Let's see an example later such so that how we can calculate this value. So we're going to take the logarithm of the likelihood function. Before taking the logarithm, let's see what's happening here. So here we have the probability of the single observation. It's the same thing. So we have this capital pi, which is multiplication. Like in summation, we have repeated sum. So for multiplication, we have this capital pi, where m is the total training samples. So total training samples is the training data number, total amount which we're gonna supply. And from I to the training sample, we just gonna repeatedly multiply every probabilities or every values. So why do we do that? We assume that the data or the events which are occurring here is independent of each other. So if they're independent, we can just multiply all the probabilities directly. So that's why we are using this capital pi and we are multiplying every probabilities. Why? Because independent events, if even A is independent of event B, A intersection B is just P of A into P of B, the combined probability. So using this formula, we can just multiply every probabilities when we assume that the event is independent. So that's what is being done here. And using this, we are just expanding this formula. So this is the likelihood function. Next thing, we are taking the logarithm of the likelihood function. Why we are taking the logarithm? Logarithm helps us to convert the product into summation. The capital pi into just product into just summation symbol. Why? Because we have the identity. We are taking natural logarithm here. So a by ab, natural logarithm of ab is ln of a plus ln of b. We have this formula, so that's why we are taking the logarithm. So why do we need to convert this product into sum? Because it is easier for computation for the models. So also it can reduce the error present in the computers. So we have something called numerical underflow. So computers, when we have a large number of digits which is near to zero, like if you multiply the probabilities, it will be like 0.000 something. So we'll have many digits after the decimal point. So in that case, the computer is not sometimes optimized to calculate those values. So if we convert this into summations, instead we'll have negative numerical values, negative large values, which can be easily computed by the computers. So that's why we are using the logarithm of the likelihood function. Now let's take the example of the scenario where we have two output variables, 0 and 1, which determines whether a student will pass or fail the exam. Using this, we can see the working of the likelihood function. As an input, we have the number of hours uh, the student studies by x. So let's say we have student 1 and 2, and student 1 studies for 3 hours and he passes the exam, and student 2 he studies for just 1 hour and he fails the exam. So this is the set of data we have here. So let's look at two scenarios, scenario A and B. In scenario A, when the input x is 1, that is when the student studies for 1 hour. In scenario A, the predicted probability is 95% that he would pass the exam. In scenario B, it is just 10% that he would pass the exam. So in scenario A, it's given the 95% you'll pass the exam, but it's not the case, right? Because in observed training data, if we study for just 1 hour, he'll fail the exam. So clearly by just naive observation, we can see that the model has been predicted, more or less has predicted the data wrongly here. So here for the student 1, let's assume the student would pass with the probability of 0.99 or 99%. And for the student 2, let's assume the probability of predicting the person would pass is 95% or 0.95, which we have it here. So this is wrong. So the coefficients in this scenario would contribute to the likelihood estimation. So let's say in this likelihood estimation formula, which is just a product of the probabilities because they're linearly independent. So we have the 0.99 and we have the actual probability as fail in the second scenario. Actual probability of this one is fail. So this is what determines if we need to use this function or this function, because we have the y I term here. It acts like activation function. So it just activates this or this based on whether if it's 0 or 1. So in this case it's 0 because student would fail the exam. In this case it's 1, that's why we write the term directly. So in this case, if the person fails, we have 1 minus this value, which is 0.05. So that's what we have here, and we get this value 0.0495. Similarly, for in this case it has predicted correctly. um, as you can see, it's just 10% of chance that this student too would pass the exam. So when the input horse is 1, we have the first student. So this input horse is 1 is for second student. So here the first student, the probability of passing the exam is, let's assume it's 85% or 0.85, but the second student is just 10%. So if we calculate the likelihood, which is just the multiplication of the probability. So in this case, also here the actual probability is 0. So that's why we multiply 1 minus this probability, which is 1 minus 0.1, which is 0.9, which we get from here. So if you multiply those two, you will get this value of the likelihood 0.765. So what does this tell? The likelihood in the scenario B, 0.765, is much higher than the scenario A, which is 0.0495. This means that the parameters in scenario B do a much better job of explaining the observed data. So the goal of maximum likelihood estimation is to find a set of parameters theta that results in the highest possible likelihood value. A perfect model that correctly classifies every data point would have a likelihood of 1, or a number which is very close to 1, as the probabilities for the each correct outcome would all be very close to 1. Here we also calculate the log of the likelihood, so which is same. So if we maximize this, it is same as maximizing this. So as we saw, this is for computational purposes. So in machine learning, we prefer to minimize the cost function rather than maximizing the likelihood, as we saw before. We achieve this by simply taking the negative of the log likelihood, which is here. The result is the cross entropy cost function. Cross entropy cost function. So this is widely used in machine learning. So why do we use this? So this is the notation. J theta is this one. Here the J theta is the cost function, and minus 1 by m, minus is the negative sign of the logarithm, and 1 by m is the negative average, so that it generalizes across different sizes or different number of data. So yeah, why do we use this? This is the function we want to minimize. So the negative sign flips the function so that the maximum of the likelihood, this maximum, becomes the minimum of the cost. So a convex loss function. Convex loss function means um, optimization algorithm. When it has the convex loss function, we'll have only single global minimum. Global minimum means globally across all the data or all the iterations of the optimization, we will find only a single value of the parameters where it can minimize this function at most. So this is represented by this cost function. So let's talk about optimization of the logistic regression model. So the first method which we're gonna see is gradient descent. So let's talk about the intuition of it. So imagine you're standing on a mountain peak blindfolded, and you want to get to the lowest point in the valley. This is the lowest point, so it's a flat point. So the only information you have is the slope of the ground directly under your feet. So this is the slope of the ground directly under your feet. So if the slope is increasing, you'll have the hill will be going upward. So if the slope is decreasing, the hill will be going downward. So you are here. So if you come here, the slope will be decreasing. So you can feel that the hill is going downward. So you have that immediate information of the slope below your feet. So how can you reach the lowest point? Your strategy would be, first we have to feel the slope at the point. So you determine the steepest downhill direction. So if it's steep this side, you will go this side, or if it's more steep this side, you will go this side. So you'll go in the direction of the negative slope. So you will take a step. So move a small distance in that direction. You'll just take a single step. So again, you will repeat the steps. You will keep feeling the new slope and taking the small steps until you feel no more slope. Here the slope will be 0 because there will not be any steepness. So, which means that you reach the bottom of the valley. So the gradient descent works exactly like this for the model. So the mountain, here this mountain, our cost function, j theta, and the slope which we have here is the gradient, and the steps which we take, the small steps which we take, are the parameter updates, the theta updates which we do. Every step we update the parameter until we get the optimal solution. So mathematically, the goal of the gradient descent is to find the values of the parameters theta such that we minimize the cost function, which we saw earlier. We do this by iteratively updating each parameter in the direction of the steepest decrease so that we can minimize this. So this is the high level overview of gradient descent. So first we need the cost function. Here we have it, the cross entropy cost function, which we want to minimize. So next step is we need to find the gradient or the partial derivative. So the gradient tells us the slope of the cost function. So it is a vector of partial derivatives. So where each derivative tells us the slope with respect to one of the parameters theta. So if we take the derivative, we can get the slope of the particular instance. So let's see how we can get it. So let's take an example of a parabola, open upward graph, y equal to x squared. We have it here. So it means that origin. If we derive this, you will get x square. Sorry, 2x. So if you plug in any x value, so let's say in this side it will be negative and this side it will be positive. So if you plug in x equal to -1, you will get -2. So it tells the negative value signifies that it has negative slope. So you can see it is going downwards. If you plug in x equal to 0, the value will be 0, which says that it is just flat. So similarly, if you put any positive values like 2, it will be 2x. If you plug in, it will be 4. So it says that it will be having positive slopes. So that's why we take the derivative of the cost function. So the next thing we want to see is that we have this formula or the cross entropy cost function. So let's find the derivative of a single training example. So this is for every training example, we take the summation and average. So for single training example, we just need to find the derivative and we can generalize it to the entire data set. So for a single example, this is the cost function. So we just have the same function without the summation and we have the same thing here. So in order to do our derivation, we just need to find another step. We just need to find the derivative of our sigmoid function. So here we have our sigmoid function h theta of x. So if we derive this, if we derivate this, we will get this right hand side equation. So let's look at it inside deeply how we can do this derivation of the sigmoid function. So the sigmoid function can be defined as this h theta of x. So we know this already, where z equal to theta tx. So this is the linear combination of the input features and the weights added by us and added together. So for simplicity, we just use the variable set. So we rewrite this for easy differentiation. This can be written as the denominator term, we just add power minus 1. So next, in order to derivate this is two functions, function inside itself. So we use the chain rule. So the outer function here is the something inside power minus 1, and the inner function is the inside itself, which is 1 plus e power minus l. So we need to if you have a function, so we just need to take the derivative of the outer function and multiply it with the derivative of inner function, which is set by the chain rule. So we have the two functions here. So first, if we derivate this one, something inside power minus 1, if we derivate this one, we'll get this one. So similarly, if we derivate the inside one, we just keep it as such here, d by dz of 1 plus e power minus l. So if we calculate this, if we find the derivative of this inner function, the derivative of constant is constant 1 is 0, so this will go, and e power minus z, this e power minus z times the derivative of the exponent. So derivative of the exponent is minus 1, that's why you are minus here. So we have the both values. So if we plug it in the original equation, so this one comes from here, and this derivative is this value, we put it here. So if we simplify that, we multiply these two, we'll get this one, this equation. So but this is not the general form, so we can rearrange the terms further. So this e power minus z by 1 divided by 1 plus e power minus z square, we can write it like this. So we can take the 1 by 1 plus e power minus z term common from this equation. So we have two terms. So if we see here carefully, this term corresponds to the original h of z itself, which is 1 by 1 plus e power minus z, or 1 plus e power minus z whole power minus 1. So we can just substitute the h power minus z directly there. So that's what in the final equation. Instead of this, we wrote the h of z directly, and for the next term, e power minus z by 1 plus e power minus z. So this we can simplify it further. In the numerator, we just add and subtract 1 here. Here we can add and subtract 1, and we can divide this 1 by 1 plus e power minus z for these two individual terms, so that we will get 1 separately. We'll get the same familiar term 1 by 1 plus e power minus z, which is the h of z itself. So we can substitute it directly. So if we do that, you'll get 1 minus h of z. So we'll have h of this term, you'll have it from here, 1 minus h of z, and this term is directly the h of z. So we'll have the h of z here. So what's the final derivative of the sigmoid function? It is the function itself multiplied by 1 minus the function itself. So we arrive at this beautiful equation. So property is what also makes the back propagation, so it's a term in neural network. So also, and the gradient calculation in our case for logistic regression computationally efficient. So this is what the property is all about. This is important, we will use it later in our derivation. Now that we saw the partial derivative of the sigmoid function, to the derivation for the actual cost function. So this is our cost function for a single observation, which we saw previously. So if we partial derivate this with respect to theta j for with respect to a single coefficient of a feature, we can partial derivate this. So here we have this is log x, log x. So log x is 1 by x. So we will have 1 by the function inside h theta xi, And using chain rule, we need to derive the inner function 2 and multiply with it. So for now, we just keep it as it is, the notation for partial derivative with respect to theta j of the inner function. Similarly, on this side, here we have log x. So 1 by x. So derivative, we have 1 by 1 minus h theta of xi inside. And using chain rule, we can derive the inside function too, for which is this one. So for now, we just keep the notation as it is. We need to find these two terms. So this one can be represented like this with chain rule. So we can partial derive this numerator with respect to z, and we can partial derive z with respect to theta j, and we can multiply them both with help of chain rule. So this notation makes our calculation pretty simple. So why? Because when we expand this term with these two, this term is much familiar to us because this is what we derived from step A, which is the derivative of the sigmoid function, which is the function itself multiplied by 1 minus the same function. So we can just directly substitute this here. And for this one, when we expand this here, so z of I is nothing but for a particular observation. We have the coefficient, which is the linear combination. So we have z as theta naught plus theta 1 of x1 feature 1 and the second coefficient and feature 2 and so on. So but here we are looking for only partial derivative with respect to a particular feature, so we'll have theta j and x, we will have the feature for it, feature with this j itself, and we'll have for I throw for a particular I throw. So this term, just because we are looking for only a particular feature and coefficient, every other only we'll have this one, and every other term will be treated as constant. So if we do the derivative, they will just be cancelled out. So what we'll be having remaining, all the terms will be 0, and we'll be having only the theta j and xi. So if we do the derivative of this one, what will be remaining is, if we do the partial derivative with respect to theta j, so this will be 1. So what we'll be having is just this one. So that's what, which is xj for a particular feature and I. So that's what is given in the answer here. So that's how we do the partial derivative of the second term in this equation. So we can just plug in that value back in this equation too. So if we combine this both, we'll be having this one multiplied by this one. So that is the value of this term. So now that we have this term, which is the product of these two, we can just plug them back into this original equation. So that is what is given by this equation. From here we get this one with help of this calculation. For this term, we can substitute the product of these two. So we have this here, we just multiply these two terms. Similarly, we have this one, so we can do the same thing here. We just substitute the same terms as we did in the left side. So here this is the same equation, just because I don't have space, I just combine them both. So after doing this substitution, here we can further simplify this equation. So in this equation, we have this. After substituting here, you can see this and this gets cancelled out. Similarly, on the part right side to the plus sign, this and this will be cancelled out. So what we have remaining is yi, this term. So this is what we have here, and the remaining term here is 1 minus yi, and this one and this one. So these three we have here, and here we have the negative sign. Here we have the negative sign, which we have it here. So now that we simplified this, let's do some more arithmetic to further simplify this. So we can just multiply this inside, and we can multiply this inside too, and we can rearrange this term, simple grouping and cancelling out of the negative and positive terms. So here we have in this equation this and this will be cancelled out, and what we'll be having in remain is this equation. So after doing the calculation, we'll have this one, and finally if we rearrange the negative sign, we'll get to this equation. So this is the final partial derivative, the single observation data of the cost function. So this one, so this is the j theta I partial derivative, this one partial derivative with respect to a particular coefficient of a feature. So this is for a single observation. So in order to generalize it for the whole cost function, what you have to do, you have to just do this summation. We have to add them all together. That's why we have the summation symbol, and we have to take the average 1 by m. So if we do that, we will get this final equation. So this is the partial derivative for the whole cost function, this equation. So this is an elegant formula. This has a powerful intuition. So we have this term, right? H theta xi minus yi. It's the prediction error. Why? Because this is what, this is the predicted value, and this is the actual label yi. So that's why it is a prediction error, which is predicted minus actual. So the full expression is just the average error. So because we take the average and do the summation, which is scaled by the corresponding feature value xj. Scaled means it's multiplied, so it is multiplied by the corresponding feature j across all data points. So so what it does is, so if we have a large average as a large error, if we have a large average error for a given feature j xj, it indicates that our model's coefficient theta for that feature needs a significant adjustment. So if we have a large error for a particular feature, this theta is less powerful in predicting the value. So that's why this theta needs a significant adjustment. So now that we derive the generalized partial derivative for the cost function, let's see the update rule, like how these features are, how these coefficients are updated. Next is the update rule. Now we can write the core of the algorithm, the update rule. So this is what we apply to each parameter in every iteration. So this update rule. So for each parameter theta j, we perform the update simultaneously. We just subtract this term. So this is what we have here, where alpha is called as learning rate, which is a small positive number like 0.01 or something that controls the size of the step which we take. So we will see what is that. So next thing, we have the partial derivative of the cost function. So we already calculated this from the previous derivation, so we can just substitute it here, this partial derivative of the cost function. So this we have here, this partial derivative is nothing but the gradient which we calculated. So what is gradient? So this tells us the direction of the steepest increase. That is, it tells the direction of the, gives us the slope. So this also can be written in this format. Here we just mention it as slope. So here, what's our objective? We just need to minimize the cost function in order to find the best coefficients theta. So if we plot this in graph here, so theta represents the coefficient, and j theta and y-axis represents the cost function which we want to minimize. So here we can see that our function is a convex open upward parabola. So this is This is gonna be our function for optimization every time logistic regression. So as we saw in starting the intuition where we have a mountain and we have to find the land by with the help of the slope at the particular instant, and we just move the direction where the slope is steepest, slopes where the slope is going downward. So similarly, it's the opposite here where we start in somewhere in random position and we just move to the point where you find the flat surface, and instead of the mountain being like this, now the mountain is like this. So here, let's take at this point, if we draw a tangent line on this curve, we can find the slope. So always the slope is like here, it's moving upward, so we have to move in the opposite direction of the slope. So if the slope is going up, we need to move in the blue direction, is the downward. So the alpha here determines the steps we take. So the small number, so if we take more steps we will move like in more direction in the opposite direction of the slope. So small learning rates lead to slow steps, and here this is what the ultimate point which we need to reach, where we have the perfect coefficients theta, where so that we can minimize this cost function. So here the cost function is minimum, so this is the point where we need to reach. So small learning rate, if the alpha is small, we'll take very small baby steps, which is slow, and but we will get the precise conversion. But if we take a large step, so if we take one step like this, another step like this, what we might skip this optimal solution, because we took the large step and we just skipped the part. So picking a right learning rate is crucial. So that's what is meant by the learning rate. So back to the moving to the optimal position. So here at this point we have more slope. As we go down, we move in the opposite direction of the slope. The slope decreases and we will eventually reach this point. So convex function in logistic regression has only one global minimum point, so that we can, global means for the entire data, and it will have only one global, so global minimum, so we can easily find just one steep curve where we can minimize this entire cost function, so we can find the parameters for the particular value. So slope here, if it is moving upward, let's take the two scenarios. So if this is the simplified function, if the slope is going upward, let's say it is positive. So here in this point it is positive, we have to go upward. So the slope is upward, so we need to go downward. So upward means it is a positive slope. So if the slope is positive, we need to subtract the parameter value. So that's why positive, and we have the negative sign here. So it will be negative. So if we subtract the parameter value, we can move downward actually. On the other hand, if the slope is negative, so if the slope is negative, you will have negative here, negative, and negative will have positive. So we will increase the parameter. So either way, this formula handles the movement of the parameter towards the global minima, this optimal point, no matter the sign of the slope. So that's the importance of this formula. So that's how we do the gradient descent. We just move slowly by taking steps on the opposite direction of the gradient until we reach the minimal point of the cost function, so that we can get the optimal solutions for the coefficient. So in starting, we saw intuition, right? Moving in the direction of the steepest curve from a mountain in order to reach the bottom part. So what if there is like two peaks? So here in this case, if we have to, this is the point which we need to reach at end. But once after we come here, we saw a flat path. So we automatically assume that we reach the end. But there is like another big curve, so which we need to cross in order to reach the end. So this is what is called as local solution, and this is the global solution. So this is what we talk in the context of local and global minima. Minima here is minimizing this cost function. So we have to reach this global minima, not this. local solution. So how it is handled in the logistic regression? In logistic regression, we just don't have the local. We just only have a single global minima. Let's see, because we have a single convex function which is in the shape of u. So u has only one minimum point. So let's see mathematically how we can say that logistic regression has a convex function. So before seeing the convexity of the optimization function graph, let's look at another graph here. So this is when we have a single parameter. So this image is when we have two parameters, theta 1 and theta 2. So instead of 2D, we have a 3D like graph, and the y-axis represents the cost function which we want to minimize. So you can see like it's a paper which is curved inwards like a bowl. So here we have the slope. So slope is higher at these points. So the red is the gradient and blue line is the path. So we just move inwards slowly according to the learning rate, and the gradient or slope decreases until we reach this point where it's the global minimum where we can find the optimal solution for the coefficient. So let's look at the proof for convexity of the cost function. So we also saw the cost function for a logistic regression, which is the negative log likelihood, is the sum of individual cost for each data point. So if we show that show that the cost for the single data point for a single data, let's say for single data I is convex. So if we can show that a single data is convex, then automatically the sum of these convex functions will also be convex. Convex means they have a single global minima in our case. So we need to take a single observation. So before that, let's look at some concepts. So we already know that the first order derivative gives us the slope. So slope tells us the steepness of the function, whether it's increasing or decreasing. So negative slope means it's going downward, and positive slope means it's going upward. So this is what we get from the first order derivative. So what happens when we take the second order derivative? So in that case, we will get the curvature of the function. What do you mean by curvature? Curvature tells how the slope is changing. So what do I mean by this? Let's take an analogy. We have speed, right? Let's say speed is 5 meters per second. So this is the first order derivative. Let's just keep it. This is the first order derivative speed. So if we take the second order derivative of the speed, we'll get the acceleration. So it tells us whether we are increasing or decreasing the speed. So it's meter per second square. So it tells us if we are increasing the speed or decreasing the speed, like what acceleration are we accelerating or deaccelerating, while the speed itself is the it tells us how fast we are moving at a particular instant, which is analogous to slope, and whether we are increasing or decreasing is analogous to the curvature. So what I mean by this, so we see the straight line here, right? So we don't see any curves here. So the curvature here is 0, but we have slope. So if we have a positive curvature, we'll be having a like this, which is a convex U shape, because here the slope is going upward. So we will have a positive curvature. On the other hand, if we have the negative curvature, it is curved downwards. So the slope will be decreasing. So on the other hand, if you have a positive curvature, you'll have the increasing slope. It's like accelerating in analogous to the acceleration and speed. which we discussed before. So if we prove that the curvature is positive, we'll have this convex U-shaped upward bend. So to prove that the curvature is positive, we need to prove that the second order derivative of the cost function for a single data point is positive. So let's repeat what we need to find. We need to find that the second order derivative of this cost function for a single observation. So this is the first order derivative for the single observation, which we derived already before. So if we prove that the second order derivative is also positive, we can ensure that the curvature is also positive, and we will have a convex U shape with a single global minima, and we can prove that we have the convex shape of the cost function. So as we told, we have the first order derivative which we defined before, which we derived before. So now we have to do the partial second order derivative of this. So here we have the notation for it. So you have to derivate this again with respect to theta j parameter. So if we do that, here yi and xij are constants with respect to theta j. So what we will have here is we'll just have the partial derivative of this, because this is constant. If we derivate this term, this will go, and we will have this constant here, and we'll have the partial derivative, the same thing here. So using chain rule, we can represent this like this. We can partial derivate this with respect to z, and we can partial derivate the same thing with respect to theta j. We can represent this with the chain rule, and for this we did the calculation already previously. So this is nothing but the sigmoid derivation which we did before, which is the function itself multiplied by the 1 minus function, and this one also we saw before, which is the linear combination. So just because we are looking at the single term, we will have only x there, rest of the terms are constant. So here we have xj and xj, we square them both and keep it here, and this is the final equation. So this is the second order derivative. So if we prove that this is positive, we'll have a positive curvature and a convex function with single global minima. So here this one h theta of xi is a sigmoid function which we saw before. It has the probability values between 0 and 1, so it is obviously positive. So this is positive, and this is also 1 minus the probability, which is also positive, and this one is x theta square. So anything square is also positive or 0. So the product of non-negative terms in this case is always non-negative. So here we have everything is positive. So the second order derivative is always greater than or equal to 0. So because the cost of the single data point is convex, the sum of all this cost, the full cost function, is also convex. So we prove that they are positive, so that we will have the convex function. So this mathematical property is why we can be certain that in gradient descent we'll have a single U-shaped convex function, and we can always find the best set of possible parameters without being stuck at local minimum, because we don't have it, we just have only the minimum. Now let's talk about another method called Newton-Raphson method, which is also used for optimization. So unlike the gradient descent, where we use only the information about the slope and we take small steps towards the global minima to get the optimal solution, in Newton-Raphson method, we use the information of both the slope and the curvature, that is first derivative and the second derivative, so that we can get the information about the whole curve, and instead of taking the small steps, we take one big step by understanding this curvature and slope into the global minima, so that we can achieve the global minima sooner. But the only catch is it is computationally expensive than the gradient descent method. So instead of taking small steps, you take a one big step. So let's see how we can do this. So regardless of the method, our goal is to find the parameter vector theta such that it minimizes the cost function j theta, same thing in gradient descent. So in this method, in Newton-Raphson's method, we can achieve this by finding the root or the zero of the gradient function, just this one. If we find roots of this function, we can find the optimal solution. So how can we do that? Because recall, what does the gradient tell about? So gradient tells us about the slope of the function. So at the optimal point where we have the global minima, at this point the slope is 0. So if we equate this derivative or the slope to 0, you can easily find the values of the parameter vector so that we can directly get the global minima here. So if we find the solutions of this one by equating to 0, we can directly find the answer. So that is the key idea here. So this is what I demonstrated and shown in this formula. That is, we equate the slope or the gradient to 0. So the next thing which we use here is uh, Taylor series expansion. So this one we use this derivation for univariate when we have a single parameter. So the theta, when we have a single parameter, we go for this. So this derivation is correspond to the single parameter. So we need to find the update rule. So we need a single parameter theta. So how can we update? So this is theta original. So theta plus or something we need to do it. So in the gradient descent we just subtracted it with the learning rate and the slope or the gradient. So here in this case we also similarly need to find what is the update rule for a single parameter. So first let's talk about Taylor series. So here this is what we achieve from the Taylor series expansion of univariate system. So what do I mean by Taylor series? We need to approximate the curve. In this case we have the u-shaped curve for the gradient function, so cost function. So here we need to turn this curve or any curve, we need to approximate this into a straight line. So that is what is being done by Taylor series. So why do we do that? So it helps us to get the next position of the point at the particular point in the curve by using approximation. So let's say we have a car and we have a curvy road. So this is the car, we have the curvy road, and this is the formula for Taylor series expansion. So here this function f theta represents the next position. So car is moving this way, so just the car is inverted but it's moving in this way. So we need to find the next position. This corresponds to the next position, and this is the current position of theta of t. So this is the current position, and next we have the derivative, which is the slope at this direction. So the slope says it's going downward, and this represents the distance of the car it's traveled. So this is using this at this point, even though it is a curve, we can use this information in order to predict the next probable position by assuming this curve as a straight line. So the overall intuition of this example is that your new position, which is this one, is your current position plus the product of your current slope and the distance you travel. This is the distance you travel, which is the initial and final position, the distance you travel. So this is based on the assumption that the road will continue at the same slope. So this is obviously it is not the same slope, but we just at this point we make assumption that it will continue at the same slope. So if the line is straight line, our approximation will be 100% true because we have the same slope. But if it's curved, it will make a good approximation at the particular point. So that's why we use the Taylor series here. So here, obviously, this is the function. We need to equate this to 0 in order to find the roots. So we equate this to 0. So here, the function uh, f of theta is nothing but we have already, which is the derivative of the cos function. So here is the derivative of the cos function is the function. We assume it here. So when we equate this to 0, we can just rearrange this simple arithmetic to keep to find the value of theta. We just keep theta on one side and we just move everything to the other side. If we do that, we will arrive at this equation. So this equation is our update rule. So here, function of theta f of t, we can substitute it with our gradient function, which we assumed in start. F of theta equal to derivative of cos function or just the gradient. So we can substitute this here, and this is the derivative of the gradient. Derivative of the gradient is the second order or derivative of the cos function. So this tells about the curvature. So this is the final update rule. So the new parameter is the old parameter minus the ratio of the first derivative to the second derivative. So it tells us to take a step proportional to the ratio of the first derivative to the second derivative. So like in gradient descent, we had the original parameter is the old parameter minus the alpha times the gradient. We have this formula here. This is the update rule when we have a single parameter. So now that we saw the univariate version, let's see the practical scenario where we have many coefficients, which is the multivariate scenario, where previously the theta is just a single value, but here the theta is the vector of the coefficients. So theta is the vector of different coefficients, and everything here is the vector matrix operations. So first we have the cos function j theta. What you have to do is we need to take the partial derivative and equate it to 0, which is the first basis of Newton-Raphson's method. So this is the multivariate Taylor series expansion formula. So similarly, we had a formula for univariate. So this is the formula for multivariate expansion. So now we have to partially derivate this with respect to theta and equate it to 0. So which is given by this equation. So here, let's look at the terms which are present in this equation. First, we have theta, which is the variable which we are trying to solve for. This one. So it is this variable theta is the new parameter vector that will hopefully minimize the cost function. Next, we have the j theta, which is obviously the cost function. And next, we have theta t, which is constant theta t. So this is the current parameter vector from the previous iteration. So we just take the value from the previous iteration for the parameter vector and we just plug in here. So it is a parameter vector, we just plug in here. So we know this value already. So it is also a constant. So the next one is we have the cost function at the current parameter vector. So this is also constant. This is cost function at the current parameter vector. This is also constant. So similarly, the gradient vector, if we take the partial derivative, first all partial derivatives which are evaluated at our known point. So this point is known from the previous equation. So we can also calculate this value. So this also constant. So the another constant here is the ht, which is Hessian matrix. So this is at t represents that it is calculated at a known point theta t. So this matrix has elements where every element is represents the second order partial derivatives. So second order partial derivatives of the cost function. So every element has the second order derivative of the cost function. So this gives the information about the curvature. So the variable term here is this one, theta minus theta t. So this variable we are solving for, it represents the step or change we need to make from the current position t. So if we subtract this, we know the new position or new steps which we need to take. So that's it about the notations in this equation. So if we partially derivate this with respect to theta, this term is constant as we saw, so this will go away. So if we partially derivate this, we'll get this one. This will go away. And if you see the next term here, we have this term, partial derivative of the cost function at the current parameter, transpose multiplied by the variable term. So this term is linear with respect to linear this term. This term is linear with respect to our variable theta. So if you see, this is of the form A transpose x. A is the vector, A t is the transpose, A transpose x. So it's the variable. So derivative of A transpose x is just the coefficient. So what we have the coefficient is this one, the A. So we'll get this A as it is. And for the next term, here it is a quadratic term with respect to our variable theta. So derivative of a quadratic form. So this is of the form like half, we have half here, and this is the variable. So we have x transpose and ax. A is the matrix, Hessian matrix, x is the vector. So this, if we in the multivariate terms, so this derivative is just ax. So that's why A is the Hessian matrix and x is this one, theta minus theta t. So we have it here. So how do we get? So in normal univariate terms, we have this x times, we can take this as x times x. In univariate terms, it will become x square. So derivative of x square is 2x, and this 2 and this half will be cancelled. So but in multivariate terms, when dealing with matrices and vectors, so we have this transpose just because so that the multiplication will be compactable, so that the rows and columns can match with each other. So if we derivate that, it will behave like that, and we'll get just this one, this matrix multiplied by the x term, which is theta minus theta. So we have this here, and this we get it from here, and we equate this to 0. So after equating it to 0, we need to rearrange this equation so that we can keep the theta on one side like in univariate, and we can move everything to the right hand side. So if we do the simple mathematical rearrangement, we'll achieve this final formula. So this is the final update rule for the multivariate analysis. Look at the terms in the final update rule. So this formula tells us how to update our parameter vector. So in this case, it's a vector theta in each iteration. It combines the gradient and the Hessian. So we have the gradient and the Hessian matrix. Gradient is the first order derivative, we have the slope, and Hessian is the matrix or second order derivatives of the cost function. Here we have the current position. Current position is the theta t, and the next position which we gonna calculate or the parameter is the theta t plus 1. So this is updated vector of parameters which we are trying to find. So this is the parameter of the current parameters of the models in the current iteration. So this formula essentially tells that to find the next position, start at our current position, then subtract the calculated step. The rest of the formula defines that steps we're gonna see. So this one is the gradient as we saw. So what is it? So it is a vector of partial derivatives. So it is a vector of partial derivatives which is calculated in the position. So this gradient tells us the direction of the steepest slope we saw before. So in a cost function landscape, it points directly uphill. So we subtract this term because we want to go in the opposite direction, just we saw in the gradient descent algorithm. And the next term here we have is the inverse of the Hessian matrix. So inverse of the Hessian matrix, I already told that the Hessian matrix has the elements of the second partial derivatives of the cost function matrix. So taking the inverse transforms this information into a scaling factor. Taking this inverse, transform it into a scaling factor. So what do I mean by it? So it tells us how far to move. So if the curvature is high, that is, if the curvature is high means if it is very, the curve is very, if the curve is very steep and we have a narrow valley, the inverse will be small. So the Hessian matrix, the inverse will be small so that the step will be small. So the step which we take will be small. So this is the global minima, this will be small. So the other hand, if the curvature is low, the curvature is low means we have just a slight curve, a broad flat valley like thing. So in that case we need to take a large step. So the inverse which we calculate from Bayesian matrix will also be large. So in a way it tells us how far we can move to reach the global minima in this equation. So the key difference from gradient descent, which only uses the gradient to determine the direction, in this method, the Newton-Raphson method uses the inverse of the Hessian matrix to also determine the most efficient step size, allowing it to converge much faster. So this is the overview of this method. Let's look at the numerical example of Newton-Raphson method. So first let's talk about the numerical example of univariate. So in this case, let's take example of this function. So this is upward parabola because we are square. So here we want to minimize this function and find the least value such that the value of the x minimizes the whole function. So if you just solve this directly, we can see that the value of x of this function is minimum when we have the x is 2, because when you have 2 you'll have this will become 4 minus 4 and the minimum value which we get is 3. So this is the minimum which we can get. So our optimal solution should be 2. So let's see how we can do this. So first thing is we need to derive this function in order to get the slope. So derivative of this is just 2x minus 4, and then we calculate the second derivative so we can get the curvature. So if you just derive this again, you'll have only 2 and this minus 4 is constant. So now that we have the first order and second order derivative, let's look at the update rule for the univariate example. So to predict the next step, so the update rule is we have to find the current step or the previous step. So then we have to subtract it with the ratio of the slope and curvature. So let's start with a random guess. So let's take that our current coefficient is 5. So here when it is 5, we need to first find the slope. So we need to find the next position. So in order to find that, we need to substitute this one plus 1. So we need to substitute this one and the slope by curvature. So what's the value of the slope? If we substitute 5 here, we will have 6. If we substitute 5 here, so we cannot substitute, it's just a constant, so we will have only 2. So we will have this here 5 minus 6 by 2 is 3. You'll have 2. So we got the original solution 2 just in a single step. So that's how powerful this Newton-Raphson method is, because here you can see that the model converges in just one step and we found the exact minimum. So even by starting with a poor guess, like a random guess, this method was able to find the exact minimum in a single step. This happened because the function which we chose here is the perfect parabola, and the second derivative which we found here, which is the curvature, which is also a constant. So the model's ability to use this curvature information allows it to jump directly to the minimum. So which is the key reason it can converge much faster than the usual gradient descent algorithm, where it might take much smaller, bigger steps, small steps, and it's much slower. Now let's talk about a numerical example where we use Newton-Raphson method in case of multivariate. So here we have this quadratic function. So here we have two variables. So the optimal point, the global minima, would be a ball. Like previously we saw in gradient descent, if we have two variables, theta 1 and theta 2, we'll have a 3D where it is like in paper, which is curved inward like a bowl, 3D image. So we need to find the bottommost part of the bowl. Here we have the two variables in this function, which is x and y. So using calculus, you can find the minimum of this function, which is minus 2 and 2. So let's achieve this with the help of Newton-Raphson's method. So, so, as usual, we need to take the partial derivative of the function with respect to x and y both. So with respect to x, if we partial derivate this, we will treat y as constant, we will get this one, and partial derivating with y, we will treat x as constant, and you will get this equation. Now that we have the partial derivatives, we can find the gradient function or the gradient vector. So the gradient vector, so unlike a single value here, because we have multivariate, you'll have a vector of the gradient values. You just plug them here. So this is the gradient vector. So the next step here is to find the Hessian matrix, because this is our update rule for the multivariate example. Here we need to find the gradient, also the inverse of the Hessian matrix. So let's see what do we mean by the Hessian matrix. So as we told, it has the partial derivatives. So here we have the two variables. So that's why we have a 2 by 2 matrix. So generally, this is the formula of Hessian matrix. So if we have features from x1 to xn, this would be the generalized form of the matrix. So here, first we are partial derivating second order derivative with respect to x, and here we are partially derivating the second order derivative with respect to y, and it constitutes the main diagonal elements. And in the off diagonal elements, we have something called mixed derivative. So here we first derivate with respect to y, then again we partial derivate with respect to x. So here we first partial derivate with respect to x and y. So these are called mixed derivatives. So the diagonal elements here represent the function's curvature along each coordinate axis. Along, we saw in the 3D, we saw two axes, right? Theta 1 and theta 2, here x and y. So it tells about the curvature along each of the coordinate axis. And this mixed derivative here helps us to represent how the curvature along one axis changes when you move along the other axis. So here we have theta 1 and theta 2. So the upward axis is the cost function itself. So it tells us how the curvature along one axis, when in here's the bowl shape, imagine it's 3D. So how the curvature changes when you move along another direction, when you move along the another coefficient. So for most functions, the mixed partial derivatives are equal. So these two are same because they are continuous. So it comes from the theorem called Clairaut's equation, uh, where when the function is continuous, the mixed derivative are both same. So this is what the essential information we want about the Hessian matrix. So now that we know what is it, so let's calculate them. First, we have the single first order derivative. So when you need to derivate this with respect to x again, we will get this term. We'll have to. When you derivate this with respect to y, we'll have this term, which is 4. So we have 2 and 4. And the off diagonal elements, which is first we have to derivate with respect to y and x and y. So first you have to derivate this function, second order derivative. If we do that, you will get 0. So we have the off diagonal elements as 0. So now that we have the Hessian matrix, and we also have the derivative gradient. So let's go to the update rule. So now that we need to update these values, so first things, let's assume that we have the coefficients, we start at 0. So x and y is 0. So this is the initial point which we assume and we are starting. So if when we take the 0 comma 0 value, first we need to plug them inside this function, inside this gradient function, in order for updation. So here if we put 0 and 0, we will get -4 and 8. So this will be a vector having the elements -4 and 8. So to find the inverse of the Hessian matrix, it is easy here. We just don't need to calculate much because it is a diagonal matrix. So the inverse of the diagonal matrix is just the reciprocal of the main diagonal elements. So we have the inverse also. So if we plug this both inside this equation, we'll get this one, where theta 0 or theta naught is the original assumed weight. So just 0 and 0. So if we calculate this, we'll get the new updated coefficient. So it's just matrix and vector operations. So if we do that, we'll get 2 1 minus 2, which is what we want to get. So we just got everything in a single step. Okay. So how is this possible? Because we are using this method, Newton-Raphson method, we can find this in single iteration. So the function which we chose here in the equation is perfectly quadratic, and the Hessian matrix, which I told about, contains all information about the curvature because it's second order derivative, so that using this information it can directly jump to the bottom of the bowl. So bowl in the sense because we have two variables, so we will have the optimization function as a bowl instead of shape curve, so we can directly jump using these information. Now let's see Python code how we can implement logistic regression without using the inbuilt logistic regression model function from sklearn. So here we have the input data, they have two features, and we have the actual output data, which is a numpy array. So here we set the learning rate and number of iteration. We can fine tune this to anything. So first step is we need to find the value of the vector theta. So the theta has the parameters for coefficient for each of this and along with the intercept value. So we pass in the input, output, and the learning rate and iteration to this function fit. So this fit function is going to return us the value vector theta. So first we initialize the feature matrix X with the number of rows and columns as the sample and features. So you can imagine this just like the table of the data which we have, where each row is the row number of the data and each column as the different features. So, and we're gonna add another column of ones to accommodate bias. So we don't need to calculate the bias separately. So the calculation is automatically done here itself when we initialize it to 1. So next step is we need to initialize the parameter vector theta, which is zeros and +1 to accommodate the bias term too. And next step is we can start the iteration. So first step is we calculate the linear combination, linear value as well, which is by multiplying the feature and the coefficient added together. So just calculate the set, and after that we do this with the dot product, and after that we calculate the predicted probability, which is from the return from the sigmoid function. So here we have the sigmoid function, so which is 1 by 1 plus e power minus n. So this is the mathematical equation. So it takes the input of the numerical value and returns us the value between 0 and 1 using the sigmoid function. It squashes between 0 and 1, which we can interpret it as probabilities. So we have the value of certain x. So next step is we need to calculate the gradient, which is the third derivative and the cost function. So we saw the gradient is just this value here. H minus y is the error, which is we need to reduce. So h is the predicted and y is the actual. So we scale this, that is we multiply it with the feature vector which we saw before. So if you multiply that with the feature vector and divide it with the total sample, because we want to take the average of the all, we need to take into consideration of the all data. So after we calculate the gradient, now we can use that to update the theta value using the update rule, which is theta equal to theta minus learning rate into the gradient value. So we have the learning rate, we defined it before, so that we can find the actual values of the theta by repeating this process which fits the given data. So here we printed the learned parameters theta here. So this is the intercept, which is the bias, and we have the other two coefficients or parameters. So we have 3 in total. So after we know the theta, next step is straightforward. We just need to predict for new data. So let's say this is the new data. We initialize it with the numpy array. So next step is we pass these in data which we need to predict along with the learn theta to the predict function. So here first thing is we need to calculate the probability. So in order to calculate the probability, we do the same thing. So we just need to find the sigmoid value by passing the data into it. Also we need to use the theta. So the set value here, the linear combination here, uses the learned theta value so that it can do the accurate prediction. After that we return the sigmoid function. So output is just a probability. So we need to classify them into actual classes, like if the probability is near to 1, it should be class 1. If it's 0, it should be class 0. So the sigmoid function tells about the probability of it being the class 1. So here that's why we have the threshold here. If the threshold is 0.5, if the probability value is less than 0.5, it will be classified as class 0. If it is more than 0.5, it will be classified as 1. We can also modify this according to the problem or domain in which we are trying to apply this linear logistic regression in different scenarios. So the output will be just the predicted classes which we print here, 0 or 1. So this is the predicted probabilities, the intermediate step by the learned theta values by the sigmoid function.